A lot of solutions and mixtures has to do with the composition of matter, a topic I have a full video dedicated to on my channel. I recommend watching that one first if you're new to the topic or at any point confused in this video. The first thing that you must know is that solutions are always homogeneous mixtures, meaning that their macroscopic properties do not vary throughout. Trail mix is not going to be a solution because it is heterogeneous and not homogeneous. If I put my hand into a bowl of trail mix, there is a chance that I don't get a single M&M. Soap, however, is going to be a solution because it's a homogeneous mixture. Every time I squeeze shampoo out of the bottle, I always get the same product. Just make sure that you're aware of this distinction between homogeneous and heterogeneous. To create a solution, we need two things, a solute and a solvent. The solute is what's being dissolved. The solvent is what's doing the dissolving. To remember this, just think that the U in solute means undergoing dissolution, and that the vent in solvent means that it's doing the dissolving. The vent goes to dissolving. Or you can also just remember the two words, it's completely up to you. If I were to take table salt and combine it with water to form a solution, what would be the solvent and what is the solute in this solution? The solvent is going to be water, because water is the thing that's doing the dissolving. The solute is going to be our table salt, because our table salt is what's undergoing dissolution. The other thing we need to know about solutions is a super important rule. Like dissolves like. This means that in order to dissolve a polar molecule, we must combine it with another polar solvent. A nonpolar molecule will never be able to dissolve a polar molecule. And the same is true reversed. A polar molecule is unable to dissolve a nonpolar molecule. This is why, when you pour olive oil and water into a glass, they will form layers. No matter how vigorously you stir this mixture, when it settles, there will always be a top layer of oil and a bottom layer of water. Again, this is because water is polar and oil is nonpolar. So they are just unable to dissolve one another and form a solution. That's also why I call this a mixture of oil and water, not a solution of oil and water. Although the rule likes dissolve like is what we use to gauge whether the combination of substances will form a solution, that doesn't fully reveal to what extent a substance dissolves. For instance, lead 2 sulfate, the stuff we put in a lead acid battery, is technically soluble in water, but it happens at an extremely slow rate. In comparison, salts, such as table salt, will dissolve almost instantaneously. The solubility of a substance and the rate of solubility for different substances will be discussed in greater detail in AP Chemistry Unit 8, much further in the future. So it's not vital for you to know the solubility rates of any molecules yet. Don't stress about that. All you need to know for now is that likes dissolve like, and some general solubility rules when it comes to salts. Most ionic salts will dissolve in water, especially alkali metal salts and nitrates, which are always soluble. Like I said, you'll learn more about the detailed solubility rules later, but for now, just know that a salt like NaCl or a nitrate like potassium nitrate will dissolve readily, whereas something like calcium carbonate will barely dissolve. You also need to know what a standard solution, also known as a stock solution, is. This is just a solution with a very well-known concentration or molarity. More on molarity in a moment. To create a standard solution, you take a solute with a known mass and you dissolve it into a solvent inside of a volumetric flask. Emphasis on the volumetric flask part. If there's ever a question in AP Chemistry that asks you what tools to use to make a standard solution, volumetric flask is always the answer, every single time. The last thing we need to cover in this video are the types of calculations we can do with solutions and mixtures. There are two main equations that you need to be familiar with. The first is for molarity. Molarity is the concentration of a solute in a substance, and it's the most common way of expressing the composition of a solution. To find the molarity of a solution, we take the moles of our solute and we divide that by the total liters of our solution. The units of molarity are thus moles per liter. And make sure you're always doing it for liters of solution. Again, molarity is the concentration of a solution. Therefore, the higher the molarity of a solution, the more concentrated it is. For instance, a solution of hydrogen peroxide at 0.9 molar is what you would use to disinfect a cut on your body. It can sting, but it's not exactly going to kill you. For industrial purposes, 31.4 molar hydrogen peroxide is used. This stuff is extremely concentrated, and it will dissolve skin on immediate contact. That's why we use molarity, to describe the concentration of our solution. The other equation you need to be familiar with is the dilution equation. This equation reads, the molarity of our first solution times the volume of our first solution will equal the molarity of our second solution times the volume of our second solution. We use this equation to find the volume or molarity of a solution after we mix it with another solution. The only other thing to keep in mind for this equation is that it doesn't matter what volume you're using, as long as V1 and V2 are using the same unit. So if V1 and V2 are both using liters, that's fine. If they're both using gallons, that's fine. If V1 is using cubic meters and V2 is using ounces, that's not okay. They have to be using the same unit. Let me demonstrate these ideas with two practice problems. A student has 50 milliliters of a 6 molar NaCl solution. They dilute it with water to a final volume of 250 milliliters. What is the new concentration of the NaCl solution? So for this problem, the way to think about it is that we're starting with one solution and we're ending with a whole nother solution. So we're going to use the equation M1V1 equals M2V2. And now we just have to fill in our values. Our M1 is our initial molarity. That's going to be 6 molar. And our V1 is going to be our initial volume, which is 50 milliliters. Again, it's completely fine to use milliliters as long as we're also using milliliters on the other side of the equation. We don't have our second molarity because that's what we're solving for, but we do have our second volume that is 250.0 milliliters. And now all we have to do is rearrange our equation to solve for M2, and we will get a final answer of 1.2 molar. Our second problem reads, how many grams of KCl are needed to prepare 200 milliliters of a 0.5 molar solution? We're given molarity and we're given volume in this one, so we're going to start with our molarity equation. Molarity equals moles divided by liters. Now let's just fill some stuff in. We get 0.500 molar equals, our moles is what we're solving for, so that's going to be X. And we're given our volume in milliliters, but we want it in liters. For this, I recommend setting up a stoichiometric conversion. I know it's really easy to do it in your head, but when our problems get more complex, stoichiometry just makes life easier, and it's good to practice it. So if I start with 200 milliliters of volume, and I know that every 1,000 milliliters will give me a liter, then this stoichiometric conversion tells me that I will have 0.2 liters of this solution. Now we just have to rearrange our equation to solve for X, and we get that X equals 0.1 molarity liters. As you can see, that's kind of weird, right? We still need to take care of our units. Remember that molarity is the same thing as moles over liters. So I can just replace that molarity with a moles over liters. And now our units will cancel out, and I'm left with 0.1 moles. Make sure you don't get high on happiness and stop here. It asks us for grams, not moles, so we still need to do a stoichiometric conversion to get moles of KCl into grams of KCl. The molar mass will be 74.5 grams per mole, and that will give me a final answer of 7.45 grams of KCl. So I hope that both of those example problems have shown you the usefulness of these equations. As with all of chemistry, it's best if you have a strong understanding of how to adapt these equations to a specific problem, rather than attempting to just memorize the types of problems that require them. And with that being said, that's absolutely everything you need to know about solutions and mixtures. If any part of this was confusing, I recommend rewatching portions of the video. If it's still not making sense, just take a break and come back after. Thank you for watching.